Amdahl's law. So this Amdahl's, we talk about the Amdahl's law. This Amdahl's law is basically depends upon or follows the prince, principle of locality. Principle of locality. Principle of locality. So, in principle of locality, to measure the performance of a processor, the Amdahl's law follows the principle of locality. So, it is important fundamental observation have come from properties of programs. The most important program property that we regularly exploit is the principle of locality. So programs tend to reuse data and instructions they have used recently. They have used recently data and the instructions of a program which are used recently. So a widely held rule of thumb is that a program spends 90% of its execution time in only 90% of its execution time in only the 10% of code, in only 10% of the code. So an implication of locality is that we can predict with reasonable accuracy what instructions and data a program will use in the near future based on its access in the recent past. So the principle of locality also applies to data access, though not as strongly as to code access. So two different types of locality have been observed. One we call the temporal locality. Or temporal locality, and another one we call the spatial locality. Spatial locality. So, what is the temporal locality? Temporal locality states that recently accessed items are likely to be accessed in the near future. But whereas this spatial locality, says that items whose addresses are near one another tend to be the reference close together in time. So this is the difference between temporal locality and the spatial locality. So then, by just focusing on some common cases, perhaps the most important and the pervasive principle of computer design is to focus on the common cases. In making a design trade-off, favor the frequent case over the infrequent cases. Frequent cases over the infrequent cases. So this principle applies when determining how to spend resources, since the impact of the improvement is higher if the occurrence is frequent. So focusing on the common cases works for power as well as for resource allocation and performance. So that is focusing on the common cases. Focusing on common cases, that means which one is temporal locality, which one is your spatial locality type. So this, in focusing on these common cases, it will also improve the performance. It will improve the performance. It will improve the performance. So the instruction fetch and decode unit of a processor may be used much more frequently than a multiplier. So optimize it first. So it works on dependability as well. So if a database server has 50 disks, suppose, for every processor, the storage dependability will dominate system dependability. So the frequent case is often simpler and can be done faster than the infrequent case. So, for example, when adding two numbers in a processor, like R1 plus your R2, when adding two numbers in a processor, suppose, we can expect overflow to be a rare circumstance and can therefore improve performance by optimizing more common case of no overflow. So this emphasis may slow down the case when overflow occurs. But if that is rare, then overall performance will be improved by optimizing for the normal cases. So in applying these simple principles, we have to decide what the frequent case, and what the infrequent cases, what the frequent case and what the infrequent cases. So we have to decide what the frequent case is and how much performance can be improved by making that case faster. So a fundamental law called this Amdahl's law can be used to quantify this principle. Can be used to quantify this principle. So the Amdahl's law says the performance gain that can be obtained by improving some portion of a computer can be calculated using Amdahl's law. So Amdahl's law states that the performance improvement to be gained from using some faster mode of execution is limited by the fraction of the time the faster mode can be used. So that is, the Amdahl's law defines the speed that can be gained by using a particular feature. So what is this speed up in Amdahl's law? The speed of means, suppose that we can make an enhancement to a computer that will improve performance when it is used. When it is used, then the speed of is the ratio. Speed of is the ratio. So this speed of will be calculated as the performance for entire task using the enhancement when possible. That means if I have a task the task which is having the execution time, this period of execution time, okay, and if I enhance this task, that means whatever the repeated code is there or repeated instructions are there, if they are stored at locality, then some portion of it will be enhanced. So it may reduce this execution time to this one. So after enhancement this, before enhancement this, that gives the speed up. So the performance for entire task using the enhancement when possible divided by performance for entire task without using the enhancement will give this speed up as per Amdahl's law. Or alternatively, we can say that the speed up is equal to execution time. Here we are talking about performance, right? So the execution time for entire task without enhancement. So here is performance time. We have seen this in CPI performance also, right? So that is the performance of your X is greater than your performance of your Y computer can be written as your execution time of your y is greater than your execution time of your x. So in the similar way, the speedup can be written that execution time of your task without using enhancement divided by the execution time of your entire task using the enhancement when possible. So speedup tells us how much faster a task will be run using the computer with the enhancement as opposed to the original computer. So Amdahl's law gives us a quick way to find this speed up from some enhancement which depends on two factors. This speed up enhancement depends on two factors. Let us see what are those two factors. Okay, so one is the fraction of the computation time in the original computer. The fraction of computational time in the original computer that can be converted to take advantage of enhancement. Another one is the improvement gained by enhancement execution mode. Okay, enhancement execution mode, that is how much faster the task would run if the enhancement mode were used for entire program. So let us see this one by one with an example. So the fraction of the first case, the first factor is, the first factor of your Amdahl's law enhancement says that the fraction of the computation time in the original computer that can be converted to take advantage of the enhancement. So for example, if 20 seconds of execution time for a program that takes 20 seconds of execution of a program, suppose program P1 is taking 20 seconds time to execute, but that takes suppose 60 seconds. It takes the 60 seconds in total can use an enhancement. So the fraction is calculated as 20 divided by your 60. Right? If 20 seconds of execution time of a program that takes 60 seconds in total that can be enhanced in, so the fraction is 20 by 60. So this value which we will call as your fraction enhancement that you call 1 by 3. So that is 1 by 3 part. So 1 by 3 that means how much portion that you are going to cut 1. So you will almost get the 0.333. So this we call the fraction enhancement, and is always less than, this is always less than 1. This is always less than or equal to 1. So this is the fraction of your computation time. Means how much execution time it requires and how much time it is taking. So the enhanced time divided by the total time, how much it is taking. Okay. Second case is, in second factor, the improvement gained by enhanced execution mode, that is how much faster the task would run if the enhanced mode were used for the entire program. So this value is the time of the original mode. This value is time enhanced part means this value is time of the original mode over the time of your enhanced mode. Original mode divided by your enhanced mode. So it is simply saying that the execution time without enhancement, execution time without enhancement divided by your execution time with enhancement. So if the enhancement mode takes suppose 2 seconds for a portion of the program, while the 5 seconds in the original mode, then you will write the without enhancement mode how much it is taking 5 seconds, and with the enhancement mode it is taking 2 seconds. So that we call speed of fraction, speed of enhancement, speed of enhancement. So you can find in the first case fraction enhancement. In the second case, we said the speed of enhancement. So the execution time using the original computer with the enhanced mode will the time spent using the unenhanced portion of the computer plus the time spent using the enhancement. So that we can write in a formula that the execution time new, as said, the original computer and the enhanced mode and the unenhanced portion of your computer can be written it as the execution time for new. The execution time for new is equal to, after enhancement, is equal to the execution time of your old execution time, which is multiplied with the how much portion the fraction enhancement done that we have seen in the previous slide, plus the execution time, the enhanced execution time, that fraction enhancement divided by your speed of enhancement. So this can be written as your speed of your overall. This can be written as your speed of the overall, or the overall speed up is the ratio of the execution time. The execution time of old divided by the execution time of your new, that can be written as 1 divided by the fractional time of your fractional enhancement plus the fractional enhancement divided by your speed of enhancement. So let us see this with an example that suppose that we want to enhance the processor used for your web serving. The processor which is used for your web serving, the new processor is 10 times faster. New processor is 10 times faster. That means the execution time of your new processor is 10 times faster and computation in web serving application than the original processor. So assume that the original processor is busy with computation of your 40% of your time and is waiting for 60% of the time for your input output devices. So what is the overall speed up gain by incorporating this? That means your fraction which is enhanced, the answer for this, we can say that the fraction which is enhanced, is equal to your 40%. That means you will get 0.4. And then what is the speed of which is given to us? Your speed up enhancement is your given that 10 times the new processor speed up 10 times. Then your overall speed up can be calculated. The overall speed up, you can write the speed up of the overall will be calculated as given in this formula, that the overall speed up is 1 divided by 1 minus fraction enhancement plus fraction enhancement divided by speed enhancement. So you can write 1 divided by your the 1 minus your fraction, so that is 1 minus your 0.4, that is fraction enhancement, will be given to you 0.6. So that is 0.6, that covers your 1 minus your fraction part, plus you are having the fraction enhancement, that is fraction enhancement 0.4 divided by your speed of enhancement. The speed of enhancement is 10, so it will be like 1 divided by if you do the simplification of this, then you will get 0.64, so which is approximately 1.56. So the Amdahl's law express the law of diminishing returns. So the incremental improvement in speed gained by an improvement of just a portion of the computation diminishes as improvements are added. So an important corollary of the Amdahl's law is that if an enhancement is only usable for a fraction of a task, then we can't speed up the task by more than the reciprocal of 1 minus that fraction. 1 minus the fraction. So a common mistake in applying the Amdahl's law is to confuse fraction of time used or fraction of time converted to use and enhancement, and fraction of time after enhancement is in use. So if instead of measuring the time that we could use the enhancements in a competition, so we measure the time after the enhancement is in use, the result will be incorrect. So Amdahl's law can serve as a guide to how much an enhancement will improve performance and how to distribute resources to improve cost performance. So the goal clearly is to spend resources proportional to where time is spent. So this is the Amdahl's laws for the overall enhancement, right?